This is third module of chapter 8. In this module, we consider another important and widely used numerical method to solve ordinary as well as partial differential equation. This method is known as finite difference method. In this method, a given differential equation is converted to a system of linear algebraic equation if the problem is boundary value problem, and if it is an initial value problem, then the given differential equation is converted to a recurrence relation. By solving the recurrence relation or by solving the system of linear equation, we obtain the solution of the given differential equation. The main concept of finite difference method is to approximate the first and second derivative to central difference approximation. That means the first derivative dy dx at xi is approximated as yi plus 1 minus yi minus 1 whole divided by twice h plus order of h square, and the second derivative d2y dx2 at xi is approximated as yi plus 1 minus 2yi plus yi minus 1 by h square plus order of h square. So, these are the first order and second order approximation to central differences. Now, let us consider the second order linear initial value problem. The differential equation is second derivative of y plus px into first derivative of y plus q of x into y equal to rx, where px, qx and rx are the known function of x. With the initial condition x equal to x0, y equal to y0 and first derivative of y at x0 equal to a, where a is a given constant or known constant. I have mentioned that the function p of x, q of x and rx are the given functions, that means known functions. Now, we discretize the differential equation 2 by substituting x equal to xi for I equal to 0, 1, 2 and so on. Then the approximation is given by, or discretized equation is given by equation 4, that means second derivative of y at xi plus p of xi into first derivative of y at xi plus q of xi into yi equal to r of xi. Now, we substitute the values of first derivative and second derivative from equation 1 and 2 to the given differential equation. Then the differential equation 4 reduces to the equation 5. And after rewriting or simplification of equation 5, we obtain the following equation, that means equation 6. Note that this equation has three major terms, yi minus 1, yi and yi plus 1. These are the unknown quantities, and all other terms, that means the coefficient of yi minus 1, yi plus 1 and the right hand side are the known quantities or known values. For simplicity, we denote the coefficient of yi minus 1 by ci, which is equal to 2 minus h into p of xi. The coefficient of yi is denoted by ai, which is equal to 2h square into q of xi minus 4. Coefficient of yi plus 1 is denoted by bi, it is equal to 2 plus h into p of xi, and the right hand side is denoted by di, which is equal to 2h square into r of xi. So, using this equation or using this notation, the equation 6 becomes this one, ci into yi minus 1 plus ai into yi plus bi into yi plus 1 equal to di, and this is true for all I equal to 0, 1, 2 and so on. Note that this is a system of tridiagonal equation. Again, using equation 1, the initial condition first derivative of y at x0 equal to a reduces to this one, a equal to y1 minus y minus 1 by 2h, or it is equal, it gives y minus 1 equal to y1 minus 2 into h into a. Again, when I equal to 0, then from equation 8 we get C0 into y minus 1 plus A0 y0 plus B0 y1 equal to 0, D0. Now we substitute the value of y minus 1 from equation 9 to the equation 10. That means eliminating y minus 1 between 9 and 10, we get the value of y1 equal to this one. That means y1 equal to D0 minus A0 y0 plus 2h into C0 into A whole divided by C0 plus B0. So equation 11 gives the value of y1 because y0 is given and all the values, that means A0, B0, C0 and D0 are known quantities. The coefficient ai, bi, ci, di of equation 8 are known because the function p, q, r are known function. Therefore, all the terms of right hand side of equation 11 are known quantities and equation 11 gives the value of y0 because y0 is known. At this step, y0 and y1 are the known quantities. Therefore, the other values of y, that means yi plus 1 given by the equation 12, that means yi plus 1 equal to di minus ci into yi minus 1 minus ai into yi whole divided by bi, where xi plus 1 equal to xi plus h. That means equation 12 keeps the values of yi plus 1 for all I equal to 0, 1 up to infinity or up to any terms. So this expression gives the value of yi plus 1 for all I equal to 1, 2 and so on, because the value of yi and yi minus 1 are evaluated for values of I equal to 1 and next time for I equal to 2 and so on. So this is a recurrence relation of y's and we can determine the value of y 1 by 1. Now you consider one initial value problem. The equation is, differential equation is second derivative of y equal to xy minus 4y with the initial condition x equal to 0, y equal to 3 and first derivative of y equal to 0. And we have to calculate the value of y for x equal to 0.01, 0.02, dot 0.10. So for different values of x, we have to calculate the values of y from this differential equation. Note that in this differential equation only the second derivative is present. So we replace second derivative by central difference approximation yi plus 1 minus 2 yi plus yi minus 1 whole divided by a square, and in the given differential equation and obtain the following system of equations. That means yi plus 1 minus 2 yi plus yi minus 1 by h square equal to xi yi minus 4 yi. This is obtained from the given differential equation. After simplification, it is reduced to yi plus 1 minus 2 plus h square xi minus 4 h square whole into yi plus yi minus 1 equal to 0. So this is the reduction form of the differential equation, and the initial condition is reduces to y0 prime equal to y1 minus y minus 1 by twice h. And from this equation we have y minus 1 equal to y1 minus 2h into first derivative of y at 0 at x equal to x0. Again from the general equation to find the value of yi plus 1, we get for I equal to 0 y1 minus 2 plus h square x0 minus 4 h square whole into y0 plus y minus 1 equal to 0. Now we substitute the values of x0, y0 and y minus 1, we get y1 minus 2 into 2 minus 4h square whole into 3 plus y1 minus 2h into y0 prime equal to 0. The last term is the value of y minus 1. That is, we get the value of y1 from this equation, that means y1 equal to this expression, and after simplification it is equal to 2.99440. And the other values of yi, I equal to 2, 3 and so on, are given by the following equation: yi plus 1 plus equal to 2 plus h square into xi minus 4h square whole into yi minus yi minus 1. So, this expression gives all values of y. This is the values of yi minus 1, yi and xi. These are required to calculate the value of yi plus 1, and the value of yi plus 1 are calculated in the last column of the table, and these are the values of the variable xi given in third column. Thus, we conclude that y at 0.01 equal to 2.9999400, y at 0.02 equal to 2.997603 and so on. These are the values of y at different values of x. And lastly, y at 0.11 equal to 2.9283339. These are the 11 values of y for different values of x, and these values are obtained from the finite difference method by solving an initial value problem. Now, we calculate the error in finite difference method to solve initial value problem. Basically, the error occurs due to the approximation of first and second derivative to the central differences. Thus, the local truncation error is given by this expression. Note that in this expression the second derivative is approximated by central difference formula. The first term is occurred due to the approximation of second derivative, and second term occurs due to the approximation of first derivative to the central difference formula. Expanding the terms yi minus 1, yi plus 1 by Taylor series, after simplification the expression for error becomes e equal to h square by 12 into fourth derivative of y at I plus 2 into pi into third derivative of I plus order of h to the power 4. Thus, the finite difference approximation has second order accuracy for the functions with continuous fourth derivatives. The finite difference method is described to solve second order initial value problem. In this method, the given differential equation is converted to a recurrence relation, and by solving the recurrence relation we obtain the values of y for different values of x. Now, we consider the second order boundary value problem, and the finite difference method is applied to solve the boundary value problem. We know that the boundary value problem is a very complicated problem among all other differential equation. So, finite difference method is described to solve second order boundary value problem. Let us consider the following linear second order boundary value problem. Second derivative of y plus p of x into first derivative of y plus q of x into y equal to rx, and the equation is defined within the interval a b, and the boundary conditions are y at a equal to gamma 1 and y at b equal to gamma 2, where gamma 1 and gamma 2 are two values. That means equation 13, that means the differential equation, second order differential equation is the differential equation with this boundary condition. The entire problem is called the boundary value problem. We assume that the above boundary value problem has a unique solution. Now, we divide the interval a b into n equal subintervals with spacing h, that is xi equal to x0 plus ih, where I equal to 1 to n minus 1 and x0 equal to a, the starting value of x, and xn equal to b, the ending value of x. Now, we discretize the given differential equation by substituting x equal to xi. Then the differential equation becomes second derivative of y at xi, that means yi, plus p of xi into first derivative of y at xi plus q of xi into yi equal to r of xi. Now, we replace the first and second derivative by central difference approximation. These are the central difference approximation for second and first derivative, and using this approximation the equation 14 reduces to this equation. So, this is the discretized form of the given differential equation. Now we neglect the term order of h square, we obtain this equation. This is the simplified form of the previous equation. Here also note that there are three unknown quantities of y. These are yi minus 1, yi and yi plus 1, and all other terms of this equation are known quantities. For simplicity, we use the following notations. The coefficient of yi minus 1 is denoted by ci, and coefficient of yi is denoted by ai, coefficient of yi plus 1 is denoted by bi, and last term is denoted by di. Using these notations, the equation 15 is converted to ci into yi minus 1 plus ai into yi plus bi into yi plus 1 equal to di, where I equal to 1, 2 up to n minus 1. Now our problem is to find the values of yi minus 1, yi and yi plus 1 for all values of I equal to 1 to n minus 1. So this is a system of tridiagonal equations. So in this equation contains n minus 1 equations, algebraic equation, and obviously the equations are linear, and contains n plus 1 unknowns y0 to yn. But y0 and yn are the end values, that means the boundary values, that means these two quantities are known quantities, and the value of y0 equal to gamma 1 and yn equal to gamma 2 are given, and for I equal to 1 and I equal to n minus 1, the equations are c1 y0 plus a1 y1 plus b1 y2 equal to d1, or a1 y1 plus b1 y1 equal to d1 minus c1 gamma 1, because y0 equal to gamma 1, this is known quantity. So in this equation only two things, that means y1 and y2 are unknown, and right hand side is a known quantity. Similarly, when I equal to n minus 1, the equation is this one, c n minus 1 y n minus 2 plus a n minus 1 y n minus 1 plus b n minus 1 y n equal to d n minus 1, or c n minus 1 y n minus 2 plus a n minus 1 y n minus 1 equal to d n minus 1 minus b n minus 1 into gamma 2, because y n is equal to gamma 2. In last equation also there are two variables, two unknown quantities, one is yn minus 2 and other is yn minus 1. Now the system of equations can be written in matrix notation as ay equal to b, where y is the column vector y1 to yn minus 1, b is the right hand vector given by this expression, and a is the coefficient matrix, and note that the diagonal elements of this matrix are a1, a2 up to an minus 1. The upper diagonal elements are b1, b2, b3 and so on, and lower diagonal elements are c2, c3 up to cn minus 1. So equation 18 is a tridiagonal system of equation, and this equation can be solved by any method described in chapter 5. Here y is an unknown column vector. This is unknown, we have to find the value of y, and the vector b and the matrix A are known quantities. Thus equation 18 is a system of linear tridiagonal equation containing n minus 1 variables y1 to yn minus 1, and it has n minus 1 equations. So we can solve this system of equation, and there is a possibility for the unique solution. This system of equation can be solved by any method. The solution of this system, that is the values of y1, y2 up to yn minus 1, are the approximate solution of the given boundary value problem at x equal to x1, x2 up to xn minus 1. Now we consider one boundary value problem. Second derivative of y plus first derivative of y plus x equal to 0. With the boundary condition x equal to 0, y equal to 0, y1 equal to 0. That means the value of x is 0, y is 0 and y at 1 equal to 0. The boundaries are 0 and 1. In this case, nh equal to 1, that means h equal to 1 minus 0 by n. The difference scheme is this one. This is the approximate value of the given differential equation, and this approximation is obtained by central difference approximation of first and second derivative. After simplification, this expression reduces to equation 19, and the equation 19 is valid for I equal to 1 to n minus 1. And the boundary conditions are y0 equal to 0 and yn equal to 0. So, using these two values, for n equal to 2, we get h equal to half, x0 equal to 0, x1 equal to half, x2 equal to 1, y0 equal to 0 and y2 equal to 0. The last two values are the boundary values of the given problem. And for this case, that means for n equal to 2, the difference scheme is this one, y0 into 2 minus h minus 4y1 plus y2 into 2 plus h plus 2h square into x1 equal to 0. After substituting the values of y0, y2 and x1, we get minus 4y1 plus 2 into 1/4 into half equal to 0, or y1 equal to 0.0625. So, this is the value of y1, that means the value of y when x equal to half. Finally, y at 0.5 equal to 0.0625. Now, we divide the entire interval into 4 parts or 4 sub-interval. That means, we assume that n equal to 4. In this case, h equal to 0.25, x0 equal to 0, x1 equal to 0.25, x2 equal to 0.50, x3 equal to 0.75 and x4 equal to 1.0, and the initial conditions are y0 equal to 0, y4 equal to 0. So, in this case, the equation 19 becomes these three equations. After substituting the values of y0, y4, x1, x2 and x3, we get the simplified equations. This equation contains 3 unknown, y1, y2 and y3, and it has 3 equations. So, you can solve this system of equation by any method, and solving this equation we get y1, which is the value of y at 0.25, it is equal to 0.043510. Value of y2 means the value of y at x equal to 0.50 equal to 0.063462, y3 equal to 0.051205. So, this is the solution for y at x equal to 0.25, x equal to 0.50 and x equal to 0.75. So, this is the solution of the given differential equation. Now, we calculate the finite difference error in finite difference method for boundary value problem. The local truncation error of this method is similar to the error occurs in initial value problem. That is, this method is also of second order accuracy for functions with continuous fourth order derivative on the closed interval a b. It may be observed that when h tends to 0, then the local truncation error tends to 0. Therefore, the more accuracy in the solution can be achieved by taking small h. But when h is small, then the number of algebraic equations become large and hence need more computational effort. So, this is the drawback of boundary value problem by solving finite difference method. Now, we discuss the stability of finite difference method. For this case, we consider the following simple second order differential equation. This is called the standard or model second order differential equation, which is given by equation 20, where k is a constant and very large in comparison to 1. So, k is unknown quantity, or it is called the parameter of the differential equation. Now, the central difference approximation of this equation is given by equation 21. The solution of this difference equation is yi equal to c1 plus c2 whole into 2 minus kh by 2 whole to the power I, where I equal to 1, 2, 3, 4 and so on. And C1 and C2 are the constant. These are the arbitrary constant and their values are to be determined by the given boundary conditions. So, this is the solution for the equation 20. The analytic solution of the given differential equation is yx equal to a plus b into e to the power minus kx, where a and b are arbitrary constants. These values can be determined by the boundary conditions. Now, note that if k greater than 0 and x tends to infinity, then the solution becomes bounded, that means solution becomes a. That means the term e to the power minus kx is monotonic for k greater than 0 and for k less than 0. Thus, it is expected that the finite difference solution is also monotonic for positive k as well as for negative k. It can be shown that the exponential term of equation 22 behaves monotonic for k greater than 0 and k less than 0 if h is less than mod of 2 by k, that means the absolute value of 2 by k. This is the bounds, upper bound of the step length h. So, this is the condition for stability of the finite difference scheme. So, under this condition the finite difference scheme gives the stable solution. In this module, we have described finite difference method to solve second order initial value problem and second order boundary value problem. We have seen that the finite difference method converts the given second order boundary value problem into a system of tridiagonal linear equations, and by solving this system of algebraic equation, we obtain the solution of the given boundary value problem. This method can also be used to solve third order, fourth order and any higher order boundary value problem. In next module, we shall consider another good method to solve boundary value problem known as shooting method.